This morning I'll be talking about Linux-As-Bootloader first, and Ron will be talking about uroot after that, so the two presentations play into each other very nicely. Let's get started. And before I get started, quick shout out to John Lewis. You all know him from the coreboot on Chromebooks community, and he also authored a thing called JELTKA, which I'll be talking about. He wasn't able to make it to the meeting, but he did put together a few slides, which I've incorporated into my deck. So I'll be covering some of the stuff that he would have liked to present. All right, so Linux-As-Bootloader. We're all pretty familiar with how Linux kind of does stuff. That this is just kind of a boot flow. Core boot goes through the boot block, does CPU in it, power stuff. It might talk to a PMIC to bring up power rails. Might do some peripheral initialization, especially on the ARM and embedded platforms where you need to set up a lot of things such as your clocks and your pin muxes, just so that you can set up the SPI peripheral and then read ROM stage and go on. And then, of course, things flow, and eventually you get to RAM stage. And one thing that I'm finding that's particularly relevant to Linux-As-Bootloader is that in RAM stage we tend to be initializing a lot of stuff that coreboot doesn't actually use. It's mostly intended for the payload to use, and in particular for Chromebooks for things like displaying the recovery mode screen or the development mode screen. Stuff that we don't fundamentally need in coreboot, but we initialize anyway for the payload. And then live payload uses that, of course. It might do even more device bring up. Might read a kernel off of an SD card or a USB flash drive or over a network. And then you load your OS kernel, like Linux, and it does a lot of the same stuff over again. The main difference, I hope you can see my mouse pointer. So the main difference is that in the payload, you generally only support these devices, and you only do this work for a very specific purpose. So like I mentioned for Chromebooks, we only go through this whole pain and agony of bringing up the display just for the niche case where we need to display a recovery mode screen or a development mode screen. And anybody that's worked in graphics, like Ron, can tell you that it can be a lot of work. And then, this is something that Linux does very well because obviously people use Linux all the time in their, after their device is booted up. So there's a lot of people looking at that code, and it would be nice if we can kind of leverage their work a little bit more. A little bit more about payloads, as we all know. Live payload provides some common library functions. You get malloc, you get CBFS, coreboot tables get passed through there. You get some hardware-dependent stuff. So when we added the ARM architectures, we had to add things like cache management to flush dirty caches and whatnot. And we have USB and some basic networking support. For Chrome OS, that's also kind of for those niche cases where you're either net booting a kernel or you want to recover your device. And actually, even with the more recent platforms, especially with the more recent platforms, USB gets a little bit more complicated, and we find buggy controllers, and Mr. Nuke here is laughing, and it's one of those things where the kernel guys may have figured it out months ago, but then we only find out after our testing team has tried to boot into recovery mode 1,000 times or whatever that, hey, sometimes if the cosmic rays hit your device just right, then it doesn't load USB, and you got to do something. I don't know, some black magic. So again, it's one of those areas where it would be nice to somehow not have to write it ourselves and instead use what the Linux people have been doing. And that's where Linux-As-Bootloader comes in. Linux-As-Bootloader was originally called LinuxBIOS, where, of course, the idea was to have, at the time, LinuxBIOS, now coreboot, situated on the firmware ROM aside with a Linux kernel. We called it a phase 1 kernel. I'll get into that in just a little bit, because it would use Linux as a driver, basically, a very stripped down Linux to load another kernel and then switch to it. I believe at the time it was called 2-kernel Monty, and then maybe some of that code got munged and reused and turned into kexec, or maybe Eric Biederman wrote it all from scratch again. I don't know. So the nice thing.
Scratch.
Okay. So on your boot ROM, you can have a kernel and you can have a little embedded environment if you want. The embedded environment, I personally like BusyBox, but you can really do anything you want there. Or you can just make it a simple script that just does one thing. Like, well, I'll get into some use cases in a moment. And of course, the idea again is to have fewer drivers that you need to write specifically for firmware. And leverage Linux as much as possible, because that's where a lot of companies throw a lot of developers. Typically, well, from what I've seen anyway, the kernel teams at some of these companies tend to be fairly sizable, a few dozen people, and the firmware team, you might get like 2 people or maybe 3 people if you're lucky, and they just want to get their stuff done and then ship the product and then forget about it. So it's good to leverage Linux just because it has a lot of momentum and a lot of development effort behind it. Of course, this idea is not specific to Linux, and in fact, I think Ron was booting a Plan 9 kernel instead of Linux. And just any kernel will do, so long as it knows the hardware well enough to get to the next stage. So it knows the hardware well enough to load your next kernel over the network or over whatever storage media you happen to have in your system. So kind of like what I was just saying, companies, well, why Linux in this case? It can do a lot of device initialization, has a huge community behind it, a lot of companies throwing their R&D into it, has a lot of users, of course, so you're going to find a decent number of edge cases. Whereas, again, going back to my example with certain USB controllers that we have support for in live payload, it's we oftentimes find issues a little bit late in the process. And the lifespan of code in the Linux tends to be pretty long too, because again, you have people who are looking at this code for months or maybe even years at a time, rather than just kind of the fire and forget model that firmware tends to be. And of course, once you already boot Linux, you have a rich set of tools. So this is kind of little redundant. So one of the nice things is, so long as coreboot can load, so long as coreboot can initialize the hardware sufficiently and get memory up and running and load the kernel into it, you're pretty much ready to start developing Linux. So if you've ever had a situation where you have a product and all the kernel developers are yelling at the firmware guys, hey, get your network driver working so I can netboot, or hey, get your SD card driver so I can boot off an SD card, or get your eMMC driver working so we can boot off the eMMC. You know how this kind of feels, and again, the firmware team is usually a little bit overwhelmed at the beginning of the product cycle, and you have to compromise. So in a way, Linux-As-Bootloader helps companies to pipeline this process such that they can almost, well, maybe not almost immediately, but start bringing up Linux on their device much more quickly. And also, once you do have Linux running in at least some capacity, you have a shell, a full-featured shell. Same thing you probably use on your workstation, so you can write scripts and test them. I'll get into some of the comparisons between these options later. And of course, you can bundle tools that you probably use in production too. So like I/O tools is this nice little thing that we have. You know, just pokes and peeks at registers and whatnot. And you can also bundle things like flash ROM and just any number of diagnostics or utilities that you might want to write for a particular piece of hardware. Of course, the biggest drawback is the size. Linux is big. Having a nice full-featured embedded development environment is gonna be pretty big too. So I like to cheat, and I have one of our lab technicians solder a nice big 8 meg or 16 meg SPI-ROM on boards that I'm messing around with, or I just have them put a socket on it, and they're very good at doing that. So so that helps a lot. Sometimes configuration can be a bear. You have to kind of be familiar with like building a cross-compilation tool chain, and you have to, of course, be good at compiling coreboot and a kernel, and you know, you can spend a couple days doing that just to get everything working right. So I want to take a quick look at kind of a typical boot flow so we can walk through this. So oftentimes you'll have coreboot, load, like Linux-As-Bootloader. This might be your phase 1 kernel with your embedded environment. And then that's going to go and fetch from some other media. Could be hard disk, USB drive, Wi-Fi, 3G, cellular, some crazy network, which we'll get into in a little bit. And then once you have that, then you load it, and that's going to be your full kernel, which boots your OS that you want to wind up in. So I'm going to take a moment to talk about JELTKA. And so JELTKA is just enough Linux to kexec another. And it kind of follows it follows this boot path, you know, coreboot, and then this whole thing is JELTKA itself. And then down here in the fetch stage, it uses Wi-Fi to load a full kernel that installs an OS. So this is something that John Lewis came up with a while back. And he wanted to be able to install Linux on a Chromebook. And he looked into using iPXE, but he wasn't quite satisfied with it. For one thing, he immediately ran into issues with wireless. And wireless, I've never written a wireless driver, but I trust that they're pretty complicated. And connection management is non-trivial. And then once you do actually have the hardware working and a connection established, everything above that is just kind of mind-blowing to me. iPXE doesn't support the most common security protocols, and you know, people who are security conscious care about that, especially if you're a business, for example, or if you really do want to boot your kernel over Wi-Fi all the time. So he came up with JELTKA. And these were some of the constraints that he was dealing with. Of course, since he was working on a Chromebook and John, he didn't want to take it apart, he was dealing with a pretty small SPI-ROM. He was using a HP Pavilion Chromebook, which Mr. Nuke is familiar with, which I believe is that a 4 meg flash or an 8 meg flash?
I think it was 8 meg.
Okay, 8 meg, but yeah, still kind of pushing the limits for an Intel system. He had to include kexec and a couple other utilities. So for him, his tools of choice were the ext file system utilities, DD, and some other things that you might just find nice to have for recovery. And also full wireless stack and WPA supplicant. So his approach was to use buildroot, and buildroot is a set of scripts that you can go download, and it'll help you cross-compile it'll help you make your rootfs. So you build your own embedded environment, and then you have the cross-compilation tool chain set up so that you can add your own little utilities in there. And like I was saying, config can be a little bit complicated, so he spent a while on that. And the main program on JELTKA is it's a script that's heavily influenced by netbootcd. So this is like a kind of a recovery sort of thing where usually flash it to a USB drive and then you boot it, and then it brings up a graphical menu and you can select which distribution you want to download and install, and then it goes from there. And then JELTKA was just doing that, but rather than depending on BIOS services, it would launch it from Linux, which enabled him to ultimately install a distro over Wi-Fi. So let's take just a moment and hope that this loads over YouTube. I'll try to skip ahead to the interesting parts. Uh-oh, I guess audio is not working on this. Okay, and it's probably skipping around a lot on the video conference. Let me try to get to where we really want to be. So here he's at CBIOS and he's talking about loading it as a floppy image. So now he's booted. This is all running off his firmware ROM. He just logged in. That's his son, who's actually at the helm typing on the keyboard while John is taking a video on his cell phone. So that little person in the picture is not John. So here's John configuring his Wi-Fi and network interface. So we go on in the video, and this is on YouTube, by the way. So if you just search for JELTKA demo, then you can find it pretty easily. So yeah, he's going through. Okay, so now he's got his wireless setup, and okay, so this is when he launches the JELTKA script and brings him to this nice ncurses menu, where he can just go ahead and install his distro from there. So a few moments later, yes, install stuff, very good. You can see it's downloading stuff over Wi-Fi, and okay, so now they're configuring it, and well, I guess I can just go ahead and spoil the surprise. He gets Ubuntu installed successfully and he boots it. And this is all done by, he just boots it, boots into his embedded environment that's stored on the firmware ROM, configures Wi-Fi, and then downloads a whole distro and installs it to the SSD. Okay, so that was kind of a one-off demo that he did. It's just really cool because it demonstrates the power that this idea can bring. John didn't have to hack up live payload to bring in a whole, Wi-Fi stack or whatever. He just let Linux do it, and it probably took him a few days rather than it would have had he tried to implement a Wi-Fi driver, which could have taken much, much longer. So with that in mind, I want to jump into some use cases. So number one, silicon vendors. As I was saying earlier, this approach can help pipeline their work. So there are fewer things that have to be functioning in the firmware before they can do kernel bring up. And as more and more stuff starts working in the kernel, once the kernel's eMMC driver works, then they can mount their eMMC or SSD. And once the kernel's network drivers work for the platform, then they can net boot. So at first it's going to be a little bit painful because they're kind of stuck reflashing their ROM every time, but it gets better. And the best part is that the code it actually gets used in the final product. So you're not you're not necessarily developing a whole bunch of stuff just to support bring up or just to support these niche cases in firmware. You're using code that's going to be used by many people for your product. Use case number 2, and I think Ron might have some things to say about this one, is for supercomputing. So LinuxBIOS was actually started long, long ago by Ron to aid with high-performance computing. You have thousands of servers, and you don't want to have to deal with some of the things that you have to deal with using a normal BIOS. Ron can tell you how much fun it is to bring up 2,000 cluster nodes and then have them each tell you that you have to hit F1 to continue. Not very fun. And more than that is that the BIOSes that came on the servers didn't really have the features that he wanted. Namely, they wanted to load the kernel over Mirrornet, which is a rather exotic high-speed supercomputing interconnect. And what they were able to do is, by using Linux, they could use Mirrornet to they could bundle Mirrornet with the they could load Linux with the Mirrornet driver and then load a phase 2 Linux kernel over Mirrornet, so they didn't have to have a whole parallel Ethernet network set up alongside their super fancy, expensive high-speed interconnect. So that eliminated a lot of cost. It eliminated space required to run the cables to each of those thousands of server nodes, in addition to switches. And every time you plug something into a machine, you have a reliability concern. For most people, if you plug something in and it doesn't work, well, you unplug it, you plug it in again, move on with life. But when you start doing this for thousands of machines, you start seeing these problems more often, and you don't catch them until the data center technician has already left the floor, so you have to send them out again. So it gets really annoying and expensive, and when you're trying to schedule a supercomputing job, then it can get really, really stressful. And of course, these high-performance interconnects are really complicated as well. So again, leveraging what's done in Linux is a pretty big win. The other thing is that for these nodes that Ron built at Los Alamos, they had no storage device. At the time, SCSI was all the rage, and so if you wanted storage in a server, you basically had to shell out maybe $500 or $600 per machine for a SCSI drive. And on top of that, to add insult to injury, you had to buy a SCSI backplane, which could be another few $100s per machine. And looks like my slide was cut off a little bit. So, to make matters even worse, disks are always the least reliable part of the machine. So, for this Mirrornet network, basically each compute node had a full list of its neighbors and other machines in the rack, in the cluster, because I guess that's because they use wormhole routing or some fancy routing technique to help reduce latency. And if a machine went down, then not only would you have problems with that machine, but its neighbors might have problems too. So failure was extremely expensive in that case. So taking out the hard disk from the equation reduced a lot of cost and increased reliability very substantially. And down here I have reduced complexity. This just refers to going along with SCSI or other certain storage media, we didn't need to worry about a SCSI BIOS or adding support to that or in our kernel or anything like that, because we just didn't touch storage. Another use case for using Linux as your bootloader, or just having your whole system embedded in Flash, is for kiosks and signage. So just like with the supercomputing, local storage is it's painful and it's expensive and it's unreliable. So eliminating local storage can reduce cost by a pretty significant amount and also increase reliability. If you're using NOR Flash, it can withstand pretty high temperatures. So if you have a kiosk, for example, one of those check-in things that you have at an airport, so you can just punch in your flight reservation and then whatever. It might be standing next to a window for several hours a day, and that window might have sun shining in it, and it can get really, really hot. And maybe the ventilation is poor, or people are banging into it for some reason. So you really don't want to have to deal with heat problems and cabling issues where some SATA connector can get jarred loose. Best case scenario is everything that's critical to the system is soldered on, so it's pretty mechanically stable, and it doesn't need a fan. So this is a good solution for that. If all your critical bits are on NOR SPI rather. Also, since you can use the full power of Linux for your networking stack, you can also boot the machine over Wi-Fi to not have to run cables everywhere. Or if you have a billboard on the side of a highway, you might just stick a 3G modem in it. Another use case, I just kind of dreamt this up the other day, is for a stateless laptop. So if you're very paranoid for whatever reason, maybe you're a military organization or a human rights organization or just a company that's really, really protective of your IP, then you have a couple different situations to worry about. If you're worried about people eavesdropping on your network, then you might want to use a hardwired network, but a case that we're hearing about more and more today is people being intercepted and laptops being confiscated. So a good way to keep them secure is to not have any sensitive information on non-volatile storage. Because once that laptop is in the hands of the bad guy, then all bets are off once you have physical access. So so the idea here is do something similar to what John Lewis did with JELTKA. Except, just add a whole bunch of security everywhere because, hey, we're using Linux and we don't have to write it all ourselves. So let's go for it. And if the laptop, you can boot up and then enter some keys to get to the prompt or whatever, and then download your next phase kernel and your OS over the network using secure channels and any number of techniques to obfuscate and secure the traffic. If the laptop gets taken and you manage to turn it off, of course, then the thief has very, very little time to retrieve any usable data from that. Because, what are they going to do? Try to suck all the bits out of RAM? It's possible, but it takes a very, very sophisticated organization to be able to do that. And of course, since there's no sensitive data stored on the laptop, the admin cuts off the laptop from any remote resources, and the thief is left with CPU, memory, a screen, and a keyboard that doesn't do much. So another use case is for OS research, and this is another thing that Ron can probably chime in on. In fact, cue Ron. So you have a minimal Linux OS that you use basically as a driver layer and a hypervisor. Your research OS tries to use the idealized drivers, and so it doesn't have to do all the dirty work. And you get more time to focus on research rather than re-implementing all the things that the Linux guys have already done.
Works for me.
Cool. So a little comparison. A lot of people think, oh, well, U-boot has all these wonderful features, or UEFI has these wonderful features, and BIOS has all these wonderful features. Especially if you get a gaming motherboard and they advertise, all the great stuff you can do in their BIOS, and then you realize, well, it's very specific to that firmware core. So like U-boot. A lot of people like the U-boot shell. That's totally fine. A lot of people like the UEFI shell. But when you have Linux as your bootloader, you get any choice of shells. You You can even get a POSIX compliant shell. Drivers, same story. Drivers for U-boot are written for U-boot. Drivers for UEFI are written for UEFI. Drivers for Linux-As-Bootloader are written for Linux. System interface, same deal. You can get something that's specific to the firmware core, or you can get something that you're targeting for your users that they're going to use and interface with every day, and you can have the full power of that, and you don't have to spend a lot of time developing something that's just going to be used for a niche scenario. Command utilities, et cetera, et cetera. Environment variables, we need to figure something out for Linux as bootloader approach, because if you're going to run utilities and stuff, then it is nice to be able to save some state. Of course, like I said, you can bundle flash ROM with this, so you can certainly write stuff to SPI-ROM, or you can mount your file system and write your state there. But it would be nice to have something as easy as like some of the U-boot variables where you just type a command and it saves a variable to SPI flash, or whatever your non-volatile storage is. Customization. So I got to confess, it's been a while since I've used U-boot or UEFI to actually build something. But yeah, trying to actually build the thing that you want to build oftentimes requires hacking a lot of make files and adding a lot of pound defines. It's pretty painful. And as much as people complain about kconfig, it could be a lot worse. So, I mean, some people like pound defines and config variables, but I personally think the kconfig, while not perfect, it's certainly better than having to find all these obscure things yourself and add them to the right place. And finally, let's see, we're getting near the end here. So I wanted to touch on user-friendliness of this approach. So, as I mentioned earlier, there's a fair bit of configuration involved if you want to build your own Linux's bootloader environment. But pretty much all the utilities and things that you need use the familiar kconfig interface. So, so the approach I usually use is to compile uc-libc and busybox myself, and both of those use kconfig. So I can run make menu config, and I go down through a list of things that I want and take off the things I don't want, and then I run make, and then go from there. It's pretty simple. So John Lewis, who made this great JELTKA demo, he's done a lot of great things for coreboot, but he'll be the first person to tell you that he's not a firmware, like a proper firmware developer, but he is a great sysadmin. So he was able to wrangle with these scripts, and he produced JELTKA just with his rudimentary knowledge of firmware and some scripting knowledge, and he made it really, really powerful. He didn't have to spend a lot of time learning the internals of U-boot or UEFI, or writing a bunch of drivers. He was able to just bundle this together just with his knowledge as a sysadmin. See, we already went through the JELTKA demo, and so that's it. So in conclusion, it's a really powerful way to boot your system, and it's surprisingly simple.